My name is Jan-Jacques, and I am a senior software engineer at MANTA and a consultant. And I'm here to tell you about how MANTA uses Neo4j graph database to track data lineage. My colleague David Bucek, he's not here, unavailable, unfortunately, but he prepared the video. So first I'm going to play David's video where he is going to explain the business use case behind MANTA. And then I'm going to show a little bit more details in depth about how Neo4j graph database enables us to achieve the business goals. There is going to be a time for Q&A after the talk, so you can of course prepare your questions ahead and I'll be here to answer them in the end. All right, let's go.
Hello and welcome to our presentation. We are from MANTA company. I'm David Bucek, leader of architecture, and my colleague who will be presenting later on is Jan-Jacques. He's in charge of graph databases here in MANTA. Our talk today is about the data lineage, tracking data lineage with graph databases. But first, let us introduce me, MANTA. MANTA is still a startup company. We started in Prague, like a startup, growing really fast. Our customers are big enterprise companies. Recently, we received nice financing. So right now, we are really hiring, really growing. We opened a few new offices. We have office in Prague, of course, in Lisbon, in Tampa, in Dublin, and trying to still grow. So what we are developing, our product, and we are a product company. Our product, it's MANTA Data Lineage tool. And we'd like to tell you today what actually is data lineage. So on the first slide, you will see a really brief introduction what data lineage is. Basically, data lineage represents a detailed map of all direct and indirect dependencies between data entities in the environment. It's a really formal way how to explain it. In normal way is just imagine the large systems and the big enterprise company have hundreds of them. And they want to know how data flow from one system to another. So basically they use a data lineage for automated mapping flows, data flows between those systems. You can imagine like that some data start and some ETL are written to the database, and from the database it flows to the reporting system. The part of data lineage is also data processing. So data under their flow could be calculated somehow, transferred, and so on. The proper data lineage can also map or, let's say, analyze and store even the data transformations. And that's the MANTA tool. So, speaking about data lineage, there are basically three types of them. The first one is a static data lineage. It's about the reading or deducting data lineage from static metadata. Let's say we are speaking about database. So we can read the SQL DDL schemas, analyze them, and deduct the data lineage from them. That's what MANTA do. The next two are runtime lineage. You can have a system which can read logs or system calls and deduct the data lineage from system calls or method calls or procedure calls. And the third type is record lineage. You can have a sound and listening actual data traffic, and you can map those data traffic into the data lineage. So that was a really brief introduction what data lineage actually is. And in the next slide, I'd like to introduce you some unique features MANTA product. We support wide range of technologies. We support 50 plus scanners from SQL databases, reporting tools, ETL tools, and also some programming languages like Java, COBOL, Python. Some of them, are in experimental stage, but as I told you, in the first place, we are growing a lot, so I will keep improving and so on. The next important feature is automated mapping. So we develop unique way how to automatically map those data, how to automatically connect them between several systems. So there is just few manual things really necessary, and we are trying our best and we are doing our best for automatization. And the third really unique feature are revisions. We are able to scan the source system over and over and record all changes in the time. And then we can see and we can work with the differences, how the systems are changed in time. I will tell you later in the real use cases. If you want to know more details about data lineage, we have a really nice ultimate guide to the data lineage on our pages. I strongly recommend you to read it. Okay, right now I'd like to tell you about some real use cases, how MANTA product can help our customers with their systems. Just first real use case. There are more than 3, but I'd like to introduce just the 3. The first one, very often, is regulatory compliance. Every big company, or most of them at least, such as banks, insurance companies, and so on, are under strong regulations. Let's say GDPR. So the regulator can arrive to the company and ask, how can you be sure that you deleted all your sensitive client's data when the client asks? How can you be sure? And the MANTA helps them to identify all places where the sensitive data is stored, and they can easily persuade and prove regulator that they are covering all those places, and if their client wants, they deleted everything from their systems about their client. So they easily can persuade and prove to the regulator they are compliant. Next is data governance. So a lot of companies in this scale and this size, the enterprise companies, have a lot of systems. I mentioned about it before. And they, very often, they are not sure about the impact. What happened if they change one systems? What happened to the other systems? And they want to be sure that they cover it and they will be safe during data migration or during the changes of some interfaces. The normal way is just send a couple of emails, try to thread everything by hand, asking developers of the other systems and so on. And of course, like they know that sometimes they receive answers, sometimes not. But if they have MANTA, they could map all those systems, and they easily know what happened if they change the interface of one systems. How will we impact the other? And the migration changes of interfaces are much easier, more error-proof. And the third use case I'd like to mention is data operations. So I mentioned before, we can record all changes in the systems. So what could happen? they could easily track what algorithm changed in the time, in the past, and how. We had one story from a client from the big bank, and they suddenly have a problem because their client, possible customer, arrived and asked for a loan, and he was rejected. And the same guy arrived in 3 months, and he was accepted. And because it was in the United States, he sued the bank for discrimination. And the bank wanted to defend themselves, of course. And they claimed they changed the algorithm. But the judge asked how. But fortunately, they had MANTA. So they could went back in time, check the algorithm, show it to the judge, and he said, okay, there is no case of discrimination. You change it from technical reasons. And our customer was able to prove it thanks to MANTA. So that's how MANTA helps our clients. Now, let me show you the very, very brief demonstration of MANTA, the part we called viewer, how the data lineage look like. Now you can see is a MANTA viewer. Here on the left part is a structure of the scanned systems. Here, as you can see on the root level, let's say, there are technologies we scan. There are like approximately 10 of them. And what I wanted to show you here is one table from graph database. In this case, Oracle. So now I'll take the one item from the tree, one table, and click on visualize, and now see how does it look like. So I can open those tables, and you will see columns, and you can easily track the source. Let's say in this case, currency code, how it flows across the systems, and to the next systems, to the final record, into where data usually ends. It's very intuitive, and it's clear how data goes through. You can use another column and track another column and so on. That's basic, simple work with this part of the MANTA systems. All right, we are here to introduce you the graph databases, how MANTA work with databases. So graph database is actually our metadata store. What we scan, what we analyze, everything is stored into the graph database. Here on this slide, graph database structure, vertical graph, we store all hierarchy of the systems. The root here in this case is a resource. It could be like an ETL tool, graph database, and so on. And under it, we have a node we call asset. It could be anything, again, which belongs to that resource, to that technology. In case of SQL database, it's table or schema. And under it could be column and so on. Here, we have a leaf asset. And leaf asset is the last in the hierarchy. And of course, in case of SQL database, this is a column. This is the last one in the hierarchy. the relationships between them are has parent. So if leaf asset is a column, has parent is a table, and between restores and the table could be schema and so on. And this hierarchy depends on the technology. On next slide is a horizontal structure. So this is a way how we actually store the direct flow in the databases. We connect just only leaf asset by databases by direct flow. And now we can see all together how it's really represented, a little bit simplified way, but how it's represented in the graph database. So there is a horizontal structure, technology hierarchy, and also flows, which are leads just from the leaf asset to another leaf asset. Here is shown how more technologies are come together. Every technology have their own hierarchy, and those hierarchies are connected on the leaves by data flows. That's how we store it in the database and where we are doing our graph database queries. What we scan, how we get the data from the source systems into the graph database. We usually start with some SQL database definition. Here on this slide, you will see create table, export card fields. We have special analyzers, and they parse it, and they create the middle product, AST. The middle product are filtered again and stored into the database in the structure we are already familiar with. So you recognize the technology, it's here, in this case Oracle. This is a table, export card keys, as you have seen before, and it's columns. And in this structure, with this structure, we can very flexibly work. We can export it, we can show it, we can transform it, and it could be shown in the viewer, in the form I showed before in the demo. Now, and this is a place I'd like to ask my colleague to continue with the presentation, and he will show you some differences between graph database and SQL database.
Thank you, David. I'm sorry for the sound quality. We'll try better next time. David showed you the interaction about the data lineage business use cases in MANTA, and I'm going to continue and give you a little bit more details about the benefits of using Neo4j graph database compared to relation databases, and how this is crucial for us because of the performance. Previously, even before I joined MANTA, MANTA used a relation database with SQL queries. Relation databases are, of course, a natural choice for common applications. However, given our data structure that David showed you in his video, you could guess that our queries are recursive in nature. This is an important factor that affects the overall performance. When using a relation database, each join using a B3 index has a logarithmic complexity to the total number of rows. And with recursive queries, the number of joins equals to the length of the relationship chain. There are some relation databases which provide syntactic sugar for graph queries, such as Oracle or MS SQL. But since the underlying data storage is still based on tables, it's not natively fit for graph traversal queries. So the syntax helps only the developers writing or reading the queries, but the overall performance of relation databases stays the same or similar. Now let's compare with Neo4j, which is a native graph database. The most important feature for us of Neo4j is called index-free adjacency. It means that relationships are modeled and stored in a way that allows traversing from start nodes to adjacent nodes without using any index in constant time. And this traversal can be in both directions. It's equivalent in performance, so it doesn't matter if the data are connected from a start node to an end node or in the opposite direction. I'm going to show you two examples of queries that we have in MANTA to compare how graph queries can look like in a relation and graph databases. In the examples, I'm going to use the same data and colors. Red are the uppermost resources, blue are the non-leaf assets such as database tables, and white are leaf assets such as columns. The first clear example is finding the asset hierarchy path in our database structure. In a relation database, there could be a table asset with columns ID and parent ID, where the ID is the primary key and parent ID is a foreign key. The data could look like this. Check the content of parent ID column. The first row is effectively the root of the hierarchy tree, so it has parent ID null. The second row is the second level of the tree, so it references the root ID. And all the other rows are on the third level of the tree, so they reference the row on the second level. Let's say that we want to find the asset hierarchy path for the asset fee amount. There are various ways for writing such query in SQL. You could write it as a loop assigning an intermediate results to a temporary table. I have chosen a recursive join for the example. I'm not sure if you are familiar with the syntax. I'll quickly highlight the important parts. There is a where condition for the starting point, the start node fee amount with ID 6. And there is a join condition where the actual recursion happens. It references the parent ID and the ID table, ID column from the same table. And this is the result. The query contains the result is the full path, in this case 3 rows, which of course can be longer in case of more detailed hierarchy. From bottom to up, there is a start row, the fee amount that we queried for. Its intermediate parent, export card fees table, and the uppermost parent Oracle database. Now, in a graph database, as you can see, there is no need for artificial parent ID for foreign key column. Relationships are first-class citizens stored in a way to allow as fast as possible traversal. The Cypher query returning the same results as the previous SQL query could look like this. The where condition is similar, but the recursion is described by pattern matching the path in here. The relationship is repeated unlimited thanks to the asterisk in the query. In real cases, sometimes it's common to limit the traversal to a reasonable depth, such as 20. But for this simple case, I'm going to show you the case with unlimited traversal with the asterisk. The result is as expected. We've got the same hierarchy path as before. Again, from the bottom to up, there is the start node fee amount column, its immediate parent export card fees table, and a database and the uppermost parent Oracle database. I'll show you how it looks like in our application. There is a tree on the left side where you can see the actual data. Sometimes it can be more nested. In this case, there is the database server and there is database schema. Here is the table, and here are the columns inside of the table. In the metadata, we can see the full path coming from top to bottom. Now going back. The second example I'm going to show you is visualizing the data flow. In our graph database structure, we are connecting only the leaf assets with flow relationships. Leaf assets on the bottom of the tree. When user wants to visualize the data flow at the lowest detail possible, for example, table columns, it's simple, going from left to right. So we just start the traversal query at the user's chosen leaf asset and follow the flow relationships and show user the result. However, when user wants to visualize the data flow at the higher level of detail, for example, between tables or even between databases, now you see that there is a potential issue. We don't have the flow relationships between non-leaf assets because it would cause unnecessary redundancy and duplication of the data. So what we have to do is to combine the flow traversal query with the other query to traverse asset paths from any level chosen by the user down and up to the leaf asset level. We start the traversal query at the user's chosen non-leaf asset and follow the hierarchy down to the leaf asset. From here, we follow the flow relationships, but at each traversed leaf asset, we have to make a side turn to find the non-leaf asset up here at the user's chosen level of detail so that we can show the results on his chosen level of detail to the user. We start the flow relationship between leaf assets only because we need the flexibility of graph queries so that we can implement and experiment with different kinds of flows. We have not only direct flows, but we also have indirect flows which represent filter conditions and other types of flows like mapping between different layers like physical or logical. As you can see, there are a lot of potential graph traversals in this query, and this is where Neo4j graph database helps us a lot with performance. I'll switch back to the demo again. I can either, I'm going to show you the difference. In the tree, user can select either a column and visualize it. So the result shows only the flows from the column to another column in talent the ETL, to another column in the ETL, and so on. But when I go back and select the table, now the visualization gets simplified. It shows the flows between from the table to talent the schema and so on. And I can choose to drill down and see the details of the flows. This is the lowest detail possible, which might be too detailed for some users. So that's why we are offering also the possibility to visualize the high-level data flows. So that's about it. We gave you a short introduction about the data lineage use case. Data lineage is a detailed map of dependencies in a complex environment, which can consist of various databases, ETLs, and reporting tools. MANTA is able to scan the whole environment with only a read access to database metadata, potentially also source codes like SQL, DDLs, or stored procedures, and create automated mapping between metadata. Based on the metadata, MANTA can show the visualization of the whole environment. And MANTA uses Neo4j because of the performance of traversing of our metadata repository and for flexibility so that we can continue evolving the product with more graph-based queries. Thank you. And now I'm ready for your questions. Let's see if there are any. Again, I have to apologize for the sound quality in the beginning, but I'm ready to answer any questions that are here.
Awesome. Thank you so much, Jan. And let's take a look if you have questions in the chat. Oh, yes, we have one. How to build a graph structure in data that does not show correlation?
Well, first of all, we rely on customers' metadata. Our customers are enterprises like banks or telecommunications, which use a lot of SQL procedures, for example, that allows us to connect the data that shows the correlation. But of course, sometimes the metadata are incomplete, and we also allow to import custom links in the database, so that if there are two separate trees in the database, like separate database and separate ETL and a separate reporting tool, and it's not connected, we allow to import custom links to show the correlation for the end users.
Got it. Awesome. And then we have one more question. I think this was related to David's talk when he was presenting. Person in back understands the use case, but he wants to understand where to start and can you start small. So if
Right.
you have anything.
I think this is hard to answer because we are really aiming at the large companies which has tens of years of legacy IT systems where employees join the company and leave the company, and there is a lot of inside knowledge that sometimes gets lost. And our tool helps the customers to map the whole environment and make it easy to understand even to newcomers. So, well, starting small, usually when you start a small application, then well, you start it from scratch and you have all details in your head, or if there is a team, then it's properly documented in case of a new application. But we are aiming at cases where the documentation is not perfect, or when we need to map the whole environment and there are gaps in it. So yeah, I'd like to start small, but it's not. This tool aims for the hard use cases.
Cool. All right. I think that's pretty much in the chat. We have the questions. Let me just see if we have more available. No, I think that's much. Thank you so much. Thanks to you and David, both for joining us at Node, and we look forward to having you for next year as well.
All right. Thank you for having me here.
Thank you so much.
See you next year, probably.
See you. Bye. Take care.
Bye.